Okay, I see. I'm comfortable either way. So this size is okay.
Or they do them first. Yeah. Can you say something? Can you unmute yourself and say something? This forever. Yeah. Putting it on the public.
I wonder how far back in the litter, like where first.
Thank you.
Thanks.
Okay, welcome everyone. Today we're really happy to have Young Bai from Wisconsin, Madison, to give us a talk about the Q-monopole-ball. Just very briefly, Young got his PhD from Yale and did his postdoc at Fermilab and SLAC. He done many works, for thinking about new physics at the various different places, like colliders, and also thinking in cosmology and astrophysics. So today he'll give us some interesting topic on Q-monopole-ball.
Okay. Okay. Thank you for the invitation, and it's great to be here. I think I remember last time I came here, maybe 2015 or 2016, but I don't remember which specific year. So today I will talk about some work in progress project, which maybe has some very detailed motivation, and I will get into that. And so this work is in progress with my previous postdoc and student, Nicholas Olarski, at current postdoc at Carleton University, and Sita Lu, and the current postdoc at Tel Aviv University. Okay, so the motivation is kind of very simple. In general, we are kind of think about new physics beyond the standard model. We are mainly think about, oh, what's the identity of the dark matter, but kind of in that kind of a process, it occurs to us that there are also a little bit less activity in terms of another interesting object, which is magnetic charged object. So in the Maxwell equation, there is no, we have electric charged particles. So therefore the del E has the electric charge density, but we don't have the corresponding magnetic charge density on the right side of that. And in some senses, the B field and the E field, they are not really can be dual to each other in the existing Maxwell equation. Obviously, natural question is why there is no additional like elementary magnetic charged particle, and then maybe you can make this more symmetric and so on. Obviously, physicists thought about this question a lot, and so in the early time, for example, the Curie was just proposed. Maybe one may have some possible to think about like some existence of a monopole, and then people just don't care, say that's a little bit unlikely, until like Dirac also use some kind of toy example to construct some monopole object. In a sense, you have some very long, very thin solenoid. Then on the top tip of that solenoid, then you can say, suppose you pretend that you don't know existence of this very strong or very long Dirac string, for example, then you only look at the surrounding this region, you say, oh, there is a monopole, point like a monopole particle there. And obviously, interesting thing pointed out by Dirac is in order to hide this, or maybe you hide can be classically, you say that's so thin, and you just don't say that. But you also want to hide that quantum mechanically, and then you put some electron go through this this circle, then you can check there is a phase change, and the phase change you want to say, oh, you don't observe that phase change, then you need to have a very specific relation and between the magnetic charge and the electric charge, which is 2 pi over E. If the magnetic charge is 1, then the corresponding coupling will be 2 pi over E, will be 68.5 E. So therefore, the Dirac kind of promote it to be a little bit more interesting, because then you can use the existence of some magnetic monopole to explain why the electric charge is quantized, for example.
Excuse me, E is the electric charge, right?
Is, yes, a coupling of the
How
electric.
come in the last equation it appears in the denominator and the numerator, and there is no dimensionful constants anywhere?
Oh, so sorry. So the E is dimension is coupling. H is also dimension is coupling.
Yes.
No dimension.
No, the beginning of the equation I understand, but the ending of the equation. I understand that H dot E is equal to some number of pi's. Now, how the last appear? Because it contains E in the numerator.
Oh, okay. So where is the pen?
Just numerically.
Yeah. I see. Yeah.
If numerically substituted, E equals to square root of 4 pi alpha electromagnetic.
Yeah.
That's
Shall I continue? Oh, yeah. Thanks. Yeah, that's the
Okay.
yeah the way to become E square. Then you put a E here. So this will be 2 alpha 1 over alpha and 2 alpha times E.
Okay.
So that's then alpha we know is 137 divided by 2. So that's give you a rough speaker.
Okay.
Okay, I see. Okay, continue. Oh, sorry, one more thing, because if the magnetic monopole is very point-like, then we know that the magnetic field is 1 over r square. Then you do a square of that. Then you have the let's say spheric, right? So you have a magnetic field square, so that's counted as energy. Then you have this to be 1 over r to the 4th, and which is 1 over r square, and the dr. Suppose you want to integrate from 0 to infinity, then you realize that there is a divergent, and so therefore this cannot be finite energy, and obviously the progress has been made in 74, which is by Toft-Polyakov. So they point out that you could, in certain gauge theory, spontaneously broken gauge theory, you could have some finite energy magnetic monopole. So let's see what's going on here. So start with some Lagrangian, which is SU2, and then you put a triplet representation. So this A is the gauge index 1, 2, 3. So this is a covariant derivative of this triplet or joint representation for SU2. This is the long-being SU2 gauge tensor. So then there is a wave, there is a potential. So usually we pretty much like take the wave, expand around the vacuum, and then study excitation as a quantum particle. But they point out that you could solve this classical equation for motion for both the scalar and the gauge field, and you potentially can have some kind of interesting structure. So let's choose some specific gauge. They call it a Hedgehog gauge. So what's going on is, so usually when we talk about spontaneous symmetry breaking, you have a 3 direction for phi, right? 1, 2, 3, A and Y, 1, 2, 3. So you choose 1 direction, and let's say Z direction or 3 direction. Then you do things around that. But here you're trying to make it a little bit spherical symmetric. You see that different direction, and you have that internal index to match to your radial direction. And so that by doing that, also you have the gauge field, which has this I is a space index. This A is a gauge index. Then you have epsilon Aij and Rj, and with some function, and that will tell you that the gauge field also kind of match to what the scalar field orientation you have, and by doing that you can kind of generally get this kind of hedgehog structure about this kind of extended solution to your simple-ish Lagrangian, and this is true if the magnetic charge is 2. You can do that in a spheric way. If it's higher than 2, you cannot get a spheric solution. Okay, just one more thing, because over there I was saying that the pure Dirac monopole, it's not a finite energy, but this one will be finite energy. So you can just go through a little bit of calculation. You have the total mass. You have.
Sorry, but the point-like charge also doesn't have a finite energy, right? I mean, so it's the very same thing. So it's usually not a problem, right? You bump it with the mass, that's usual, right? And then if you have relativistic theory, linear divergence is softened to a longer. So it's the same thing here for a massive monopole. Let's say a massive monopole point like, right? So I can in the loops, it's probably when it becomes relativistic, it's probably also softened to a lot. No?
You see, we don't have any theory, relativistic theory for quasi-classical solitons because they're relatively compact but have huge mass compared to their
so there is
Compton
no
wavelength.
regime where I can go.
So the only way to do so, it's like Zyberg and Witten, for instance. So find an effective theory, and then in this effective theory description, a monopole just a local field, and then okay, its mass diverges logarithmically. Or in the case of super young Mills, in the case of super young Mills, I believe it doesn't have even logarithmic divergence.
But it's very hard to write it's very hard to write a mutually local description
Right.
of some quantum field theory with light, electric, and magnetic particles. It's like, I don't think it's possible, really.
What you can do and what people usually do is they sum overall oscillations, small oscillation near this given monopole solution, okay? And this small oscillation, because they're expressed eventually in terms of the vacuum expectation value, which is renormalized logarithmically, they are also renormalized logarithmically, but this normalization goes into the mass renormalization. But you cannot have this picture, you cannot have anti-monopole, like in QET, you have an electron plus an anti-electron far separated in energies, and nevertheless, the contribution of the positron softens the linear divergence and makes it logarithmic.
So, but I just want to understand for myself, this is a problem is just because it's untractable, it's difficult, or it's difficult to treat because you need.
No, quasi-classically, you don't see, you don't have in this theory any anti-monopole. But if you have an effective theory, like for instance, Zyberg and Witten.
So, yeah, but if you don't have anti-monopoles, then your description is not dual, right? Because
You cannot have it just quasi-classically, because what quasi-classically does, it only gives you small oscillation near the saddle point. So you can have, so to say, dressed monopole, but you cannot have, but its mass is not linearly divergent anyway. Because the size of the monopole provides natural control.
Yeah, so yeah, come back. So then you have the B field, the magnetic field, so match to one term. So there is a gauge field, which is parameterized over there. Then you have the scalar field, which is a phi, keep tracking the field. Then you have the potential term. So then you just write down the equation for motion for those field, phi and the gauge field. Then you put some boundary condition. At far infinity, you have the here we normalize everything in terms of the wave, right, or the W gauge boson mass as the general radius for this. So such that those fields, they are dimensionless. So you just keep tracking. At a far infinity, the phi gets a wave. So it's 1. At the origin, it's 0. And also some relation for the gauge part. And so then you solve that. Then you get some profile. For example, just first look at the solid line, for example. Suppose we turn off the cortical coupling of the scalar field. So sometimes we call that is a BPS limit. So you have the reason people concentrate on BPS limit is because you could have a very, very simple analytical solution for that coupled double differential equation because you can change that to first order differential equation. And then you can just get some function behavior. So for example, the scalar field, you have this at origin to be 0, which means the symmetry is restored. And then you extend it to that. And also this general shape, transition shape is order 1 in terms of 1 over MW, tells you that the monopole radius is just one inverse of the W gauge boson mass. And so that's just some general property. And you can also center the coupling, quartet coupling to be infinity. And that one you just match to some order 1 number in terms of the total mass of the monopole mass, which is 4 pi of the wave, and divided by coupling, gauge coupling. And obviously later on, people have a little bit more deeper understanding of those existence of this magnetic monopole in this gauge. Spontaneous broken gauge theory is because of there is some like a homotopy of mapping of the internal space to the coordinate space, and then you find that there is some topological reason for that. And then there is most of the monopole which drive people to think about, oh, maybe there's some monopole in the nature, which is a grand unified theory, because that specific breaking pattern of S25 break to standard mode gauge group does match to this topological. Therefore, you do anticipate could have some magnetic Gatt monopole object, which was matched to the Gatt scale in some way. So theoretically, or in terms of a theory, you could anticipate their Gatt monopole exists. But that doesn't necessarily mean that in the current universe we have a Gatt monopole, because then you need to ask the question how you form those monopole and what's the abundance. And that's also another big, one of the bigger motivation for people to think about invention of inflation to inflate Gatt monopole abundance away. So lots of literature about that. Okay, so I will not talk too much about Gatt monopole. Let me continue. Another kind of correlated question you can ask is why we don't have a monopole just pure in a standard model, because we do have a, so I mean, simple answer to this question is because the gauge group doesn't work, doesn't work in a nice way, because we have U1 hypercharge. Eventually the unbroken U1 is a linear combination of SU2 weak and the U1 hypercharge, but this U1 hypercharge basically is not a compact long-abelian group such that you don't have a finite energy monopole. But we can still proceed. Sometimes that's pretty much it. We end up with this. So suppose we want to proceed to ask what will go wrong. Suppose we want to construct some Electroweak monopole, for example.
There is this Nambu monopole in the standard model.
Yeah, I will mention.
Okay.
Good. Yeah, very good. So this construction, which is follow Nambu, right? So basically, you could think about Higgs is a doublet. Previously, we talked about SU2. We use a triplet, right? So you could use a doublet H dagger and sigma matrix and H to construct a triplet-like object. And so therefore, you can parameterize the Higgs using some radial R dependence file, and then there are some specific theta and phi dependence. And for the SU2 weak gauge field, so you do the same thing like what we did for the Toft-Polyakov. And but for the U1 hypercharge, you just fixed. And in order for you just fix to be specific configuration. In order for the asymptotic far distance, you just have U1 electromagnetic gauge symmetry to be unbroken. So then you use that to fix. So this has been this specific ways to parameterize the possible solution has been first put out by Lambeau and also later developed by Cho and Mason. Okay. So now let's say, so we do we just put that back to the action. Then we just check a various of terms. So here I kind of separate some terms, which is the derivative of those profiles. We call it a K, which is more like a kinetic term. And also some term we call it U, which is a different term, right? So for this term, we have that in the Toft-Polyakov monopole. This first three terms in the capital U, we also have that one, but the last term, which is not. And so you can see that the last term, which is the troublesome term, which is 1 over R to the 4th, which is very similar to the Dirac monopole case. And you do integration for that, you get a divergence, and then you don't have a finite isolated monopole state basically. But that doesn't necessarily mean that there is no interesting state in the standard model. And So Nambu pointed out that you maybe can have a monopole very similar to the Dirac string now, right? So except that this string is Z string, the boson string, and connected electroweak monopole and anti-monopole together. And the general mass, which will be like a 4 pi V electroweak scale divided by gauge coupling, will be like multiple TeV. So maybe there is some chance, maybe future, but you are formed the kind of a extended object. So in general, it's not easy to produce by some proton-proton collision. So the cross section should be dropped. So that's still, I don't think people have calculated what is the production cross section for this at HSA yet. So it's still.
What's the width of it?
What's the width? I think in general, it's a very fast annihilation, and generically I would say is just MW size will be the width. So which decay very fast. And,
Excuse me, which year was this paper by Cho or Ko and Mason on the previous transfer?
1996.
96. Okay, thank you.
Okay.
But this monopole, anti-monopole, that can be produced in the early universe, though, right? If it's only TeV. So
Yeah.
you know what the effects are.
Because it's so short-lived.
See, just
yeah. So that's why the whole thing we want to looking for is something really stable in the age of universe. And I'll get into that. Okay.
Can I ask a question about
Yes.
this? Sorry, I'm unfamiliar with this Nambu solution. Is it an actual solution of the equation of motion, or is it, in other words, is there some magical length and some magical orientation of the two monopoles such that if I just keep that length and keep that orientation, it's the solution? Or is it like you stretch them apart, as soon as you let them go, they.
One more thing, there is angular momentum. You make the monopole, anti-monopole, put some angular momentum, they rotate, that will increase their lifetime, right? So usually there is, you can think about it. It's a monopole, anti-monopole bound state.
I think that Nambu himself considered the string, and then he figured out the magnetic flux of the. You see, there are two appropriate U1 bosons. You know, U1 which remains really massless, and U1 which is in the Z boson. You know, it's part of SU2. So inside the string, there is a restructuring towards the end of the string, because the real U1, which is a massless particle outside, I mean, in the perturbation theory, it emanates from the string. And he calculated the flux and figured out that it's exactly the flux of the monopole, because of course it's hard analytically to calculate near the endpoints.
I see.
If the string is infinite, you can do it analytically by solving the equation. But near the endpoints, you have to do a very hard numerical calculation, which probably was unavailable to Nambu. It was 1977. But today, it's probably doable. I don't see why not.
There is a few follow-up paper in the last maybe 1 or 2 years, trying to make more precise to get the correct detailed profiles, and so maybe if you're interested, you can check paper set. Okay, so let me continue. So now you see that we need some either one way, easy way, which is we have some BSM physics, right? Grand unified theory is one possibility. So then you make that U1 hypercharge embedded into some long abelian. Then you have some symmetry breaking. So then you can potentially have the monopole, finite energy monopole. But another possibility was you just hide that inside a black hole, because of somehow you say a black hole, there are lots of Planck scale physics you don't really understand, but then you don't ever probe inside of the black hole, and so you potentially can do that. So that is one possibility, which is that you maybe have some magnetic black hole. So this is the image of the event horizon telescope. It's kind of interesting. I want to point it out. So because they have like an accretion, so there is a supermassive black hole in the center, there is an accretion, there are lots of kind of a plasma going around. And they also have a little bit of dipole magnetic field going around here. And those dipole magnetic field can have the electron move in that and radiate some photon, then they can check the polarization of those photons to get some nice image, and also use the polarization of those photons to get some magnetic field distribution in this region. And in their simulation, they will assume that there is one monopole, another monopole, opposite monopole to do their kind of complicated simulation to calculation. But also kind of one interesting question, I don't know, probably has not been addressed is, can one have like a later magnetic charge inside this black hole, and will that give you different prediction? Which I think the answer probably is yes. And so kind of correlated question. Okay, so another thing which I don't want to talk too much because I was kind of getting a little bit interested in last year was working on the magnetic black hole. So just to give you a little bit sense, which is some similarity to what I'm talking about today. So suppose you have a QX2, which you know how to construct a spherical configuration, and you have a black hole in the center, and then you have this magnetic field outside. And the interesting thing is that the magnetic field just outside of the event horizon radius will be very large. It's much, much larger than the electroweak scale. So as a result of existence of that magnetic field, will kind of give you negative mass to W gauge boson, for example. And as a result, then that means that you need to recheck your vacuum. And result that you have the electroweak symmetry to be restored to some radius and outside of the of this magnetic black hole. And it's kind of interesting. Is like if you have a standard model, then naturally you have some electroweak hair of the magnetic black hole, and which is kind of a fun object. And also there are some additional stories when you have the additional particle falling in. If this become long-extreme black hole, the Hawking radiation is not a three-dimensional Hawking radiation, is like 1 + 1 dimensional Hawking radiation because of the fermion motion in the magnetic field behaves like a bosonic style, and so it's lots of interesting. So here we just went through a little bit of explicit calculation to solve the GR together with those gauge field, scalar field, and to get some sense what will be the profile. Again, you can say that we plot in the log scale. So in sense, electroweak W gauge boson radius is order 1 here, and then the Planck scale is basically 10 to the -17. So the scalar field will be rho r, which will be some generic, almost like a restored for most of the inner region, and then the gauge field is fr, and the metric has some 0, so have some event horizon, then going up to be not care about curved space after a while. So in principle, those things can be in the QX2, you can solve that precisely and put a standard model in jar. And okay, so but for QX2 bigger than 2, and also some kind of proof, almost like by Guth and Weinberg in 76, trying to say that you cannot have a spherical configuration for your magnetic object, and it's a little bit slightly involved. I don't think that I can have a simple statement to say why. Eventually, it's trying to match some angular momentum match, and such that you only in QX2 you can have a nice match, and you can have a spherical configuration. But in the large Q, you cannot. So therefore, if you have a very large magnetic charge, then the hair will be a little bit of with some shape, non-trivial shape, nobody knows, and but inside that you will have the electroweak to be restored. Outside of you have the ordinary electroweak broken vacuum, and generically you anticipate the black hole mass will be some cosine theta w of some ordinary extreme electric charged black hole mass, and multiplied by whatever the charge.
So are these supposed to be primordial or produced from an astrophysical object?
Even for this object, right?
Yeah.
So in my mind, it will be primordial, and but let me just think about astrophysical, because if it's astrophysical, we still need to first have also some monopole. Let's say, suppose you do have some very small fraction, small density of Gatt monopole, right? Suppose we have astrophysical black hole, then that may be the Gatt monopole maybe getting inside the black hole, and that will be charged. But for those astrophysical black hole, they are so heavy, solar mass, right? So, but here you can see that when you have the inside, you have the event horizon radius. When the event horizon radius is larger than the electroweak radius, then there is no hair, no electroweak hair. So you just have ordinary electric charged black hole. So because of that, and the black hole mass has to be like less than or around like Earth mass, and so only for Earth mass. In magnetic black hole, you anticipate they should have a hair, and otherwise you don't have. So from that point of view, I would say, yeah, should be.
So you're saying that there should be some concentration of monopoles somewhere in the universe for these things to form.
Oh, that's what I'm saying. I'm saying that
because then there's inflation, right? I mean, inflation would have removed all these monopoles.
Okay, so yeah, if you only have a GATT, the answer probably yes. But you have others like GATT symmetry first break like what is like PS Patisalam, for example, right? There are some intermediate additional breaking lower scale. You can also produce a monopole later stage.
You're still imagining reheating to some threshold
which you can produce after inflation. Yeah, then you can get those objects. Yeah.
Why doesn't the astrophysical black hole with monopoles have hair?
Oh, because their radius, because suppose they are black. Because if they are if they are solar mass and black hole, and the radius is too large, such that the magnetic field on the radius on the event horizon is so small, such that you don't prefer to restore your electroweak symmetry.
What do you have if you are dealing with regular black holes, which are those which have been observed, which are of a huge radius?
Yes.
So what, and you want to combine them somehow, I don't understand, somehow with monopoles.
Yeah.
That's what you want to do.
No, but I don't understand.
So the monopoles are trapped inside black holes.
Yes.
But we will never know that.
We never know.
Well, you could in principle. I don't.
If the charge is large, if the charge is large, we will know.
Yeah. Well, it depends what you mean by large. There's going to be a limit anyway. But so why isn't it like Reisner-Nordstrom? Just
it is for the so that's a condition I'm talking about here, right? So if we have an extreme black hole, if its mass is bigger than around like Earth mass, it's just ordinary extreme Rm black hole. You don't, but if you have the mass to be smaller than the planet mass, then you have more interesting electroweak hair. That's.
Yeah, but you have the hair even if it's big, right? I mean, Reisner-Nordstrom, you have the electromagnetic hair, right?
No, we don't call that hair.
They are electric, right?
Yeah.
I'm talking about the electric charge.
Sorry.
Because you don't have none. But if you have monopoles, then you would have both.
Like you have
Like diode, right?
Dionic black hole. Yeah.
Yeah.
But those are
Black
solutions
hole.
that you can write.
Of course.
So it's just a convention, just a language issue. We don't call that electric charge or pure magnetic charge to be hair. We call it Rm black hole. Okay, that's probably the one. Okay,
There's fields.
Yeah, sure. Yeah, the hair I'm talking about like a scalar hair, and there is a Higgs profile, and for this electroweak hair. So
not gauged hair.
Not gauged hair. That's what. Yes, that's what I want to. Yeah, it's just language issue.
So what is the mass of the black hole when this radius where this thing restores becomes comparable with the additional radius?
Which is
The Earth mass.
Earth mass.
So the monopole production has to occur relatively recently, after all inflation is gone, right?
Yeah, should be after, yes.
Because normally we say monopoles, if they are born at very short times, okay, after Big Bang, they are inflated away, and in a visible part of the universe, we can see at most one, maybe nothing.
That's correct.
But now you have to populate black holes with the monopoles. So
yeah, which is Tony's question. So we need a reheating temperature to above your gauge symmetry spontaneous breaking scale. And,
Then how do you avoid the standard problem again that you don't have too many of them?
So again, if the intrinsic symmetry breaking scale is not a GATT scale, 10 to 16 GeV, for example, even for the ordinary calculation, if it's like a 10 TeV, it's okay, it's allowed. Right? Just calculate abundance eventually is still proportional to the symmetry breaking scale.
But then, if this is true, if it is easy to form monopoles, why should I focus on the monopoles only inside the black stars? Then this is a rather rare occurrence that a newly produced monopole happens to be along a black star of the reasonable size in order to swallow it. Then there will be many of these newly produced monopoles not swallowed. And then, if this is true, if we can find them, we can bring 1 kilogram of monopoles here to Earth, and this will, through catalysis, it will solve all humankind's energy needs for the million years ahead.
So we can get into the So
once I gave this problem, when Rubakov and Callum came up with the catalysis, I gave this problem as a diploma project for one of my students. And he came and said, okay, 200 grams of such monopoles and forget about energy needs.
So, sorry, in principle, we could just not talk about black hole or whatever, just talk about isolated monopole. In general, yes. I think the one kind of phenomenological motivation is like, or maybe we want to get a little bit large charged magnetic object, and not just unit charge. And so that's the reason, because the same charged magnetic monopole, they don't stay together because of the repulsive force, right? So then you ask, the black hole will do that because they just use gravitational hold them together. So what I want to show you another case, which is some other things can also hold them together, not a black hole. Okay, so that's what pretty much I just mentioned. The rest. So you could use gravity to hold multiple charged monopole together. But just one more simple point I want to make is you have the magnetic monopole. Then you can think about the exchange force between those two, and you have a gauge force, same charge, repulsive, but you also have a scalar force because there is a scalar field. So in the BPS limiter, when you make the cortical coupling of the potential to be 0, and the scalar is also massless, so you can also like a long-range force, and they cancel each other such that there is no force in the BPS limit. And but once you go slightly beyond the BPS limit, then the scalar has a mass, then the attractive force will be weaker than the repulsive force. Then you still anticipate they repel from each other. You don't anticipate they want to hold together. Okay. So the one thing we, because of some phenomenological reason, we want to ask ourselves is how can we have some other ways to have a large magnetic charged object. Because if it's just a black hole, then you have a little bit of Rn black hole kind of relation. Then you have the mass over charge is just a Planck scale up to some coupling, gauge coupling. And so that's totally determined. But suppose you want to question with us is like, can we have some more freedom? The mass is mass, the charge is charge, maybe some other scale to distinguish that. So then that get into this kind of Q-monopole. So simple thing is like you could throw monopole inside another object, which is Q-ball, I will define, which is another non-topological object. Then you can put a multiple monopole inside that Q-ball, then they still will be okay. They will not come out. So eventually it's just some kind of, instead of like gravitational pressure, is some kind of vacuum pressure to hold those objects together.
So you want to make a Q-ball out of monopoles?
No. I'll give you the ingredients. Sure. Okay, that's okay. First, in case some other audience people don't know about Q-ball, and which is non-topological soliton. So they're first extensively studied by TDNI, later on by Coleman, and basically you can have some, once you have a conserved charge, some U1 charge, global charge, and then you can find some extended object, and those objects could be the lowest mass per charge state. So therefore, that state can be stable even at quantum level. Okay, because so that's the general idea. But just what you need is just in principle, if you only have one field, a complex scalar, what you need is a little bit of non-trivial potential. That's all what you need, and also conserve the U1 symmetry. So that's what you need. So for example, here you can see this potential no dimension, right? So, which is in Coleman's paper. So there is a phi square 1 minus a phi square square. So which you say is a funny way to write this potential. It has a dimension 6, dimension 2, and a dimension 4, right? So dimension 6 is important to give you some non-trivial wiggles in the potential. And then you have the global minimum, which is 0, and no symmetry breaking, and then, but you could also have some other metastable minimum over there, and then you can ask yourself where the matter or the Q charge wants to live in this vacuum or live in that vacuum, and he basically performed a simple calculation for that.
If I take higher dimensional operators in its whole generality and add them to the Stern model, and we'll take them seriously, not as perturbation, but here like a very, 100% effect. Would there be something like stable number things? Because the previous analysis of the Stern model was probably for the minimum dimension 4 Stern
Yes.
model, right? So if I extend it by dimension 6 and take it seriously, right? Not as perturbation, maybe there are some solutions that are missed.
The answer is yes, which I can very briefly mention, right? So you just the easiest way is you extended the gauge sector, right? So you want hypercharge embedded into some non-linear, for example, right? Or you can even add additional interaction, some higher dimensional operator, say
same field content, but
okay, higher dimensional, it can be done, I think the Cho, Mason, and one of those two persons, they still go in that direction and add some derivative, and also some paper by Johnny's also was trying to analyze or some model like higher dimensional operator they need to solve to make it a finite electroweak monopole, and turns out could just predict too much for Higgs physics and so on. So there's some study like that. Yeah.
You have a little bit of intuition for this. Like essentially what this is saying, I think, is that you generically expect there to be some binding energy.
That's right.
So why would there necessarily why would it be the generic thing that you have binding energy? Or like random potentials? Like how do you know it's not going to be repulsive? Because how do you know that this is true? Like you can draw potential where this is true, you can draw potential where it's not true naively. So how do you know it's true?
That's right. Coleman's paper specifies.
Okay, so
the potential.
okay,
But then again, to your question, because then it seems like you're just making stuff up about.
Yeah. Very good. Let's go into detail and first go through what his calculation. Okay, so you have a different chart, right? So you have a phi, you have a put some frequency, the time part, then you isolate everything is spherical for this calculation, right? So you have the charge related to the omega, this volume, r whatever size, radius, square, cubic, right? So you can calculate there is the time derivative part of the energy of the total mass, and you just use the charge to get that term, which is just a phi dot and the square term, right? And then there is another, which is the vacuum energy or the potential energy part times the radius. Then you do the variation of that. Okay, so you do variation to the size. Then you will determine the size. Then you substitute back. Then you will realize that the energy will be goes like a square root of 2u, whatever you have, and over phi square. So as a result, you want to say, oh, I want the lowest energy per charge state. So instead of looking for smallest vacuum potential position, but you are looking for the potential over phi square. So phi square in some sense is taking into account some mass term. So what you're looking for is minimum of the potential over phi square, right? For the potential, I was just drawing, or he was using. So the potential, you draw here, right? So the potential is same potential, but you also can plot what is the potential over phi square. Then you realize, oh, actually, it refers to in that metastable point. Okay.
Can we think about this the following way? Like to introduce a charge, one thing you could do is you could introduce a chemical potential. Right?
Yes.
And then for certain values of the chemical potential correspond to particular charges.
Yes.
But the way chemical potentials enter the effective action is essentially as a negative mass square. So that means that whatever you assume for the shape of the original potential, once you introduce the chemical potential, you might produce the configuration that you're drawing there. You'll produce some dip somewhere.
Very good. Agree. That's the idea. So yeah, I think that's.
I haven't looked at this paper in like
a long time ago, right? So yeah, that's right for the idea. So
Sorry, this dimension 6 term is suppressed by some scale.
So here no scale. So don't worry about it. I just immediately give you another little bit. You don't better Lagrangian. You don't need to ask. Don't care about this dimension 6 operator.
I see.
Okay, so very shortly, and so you say this is hard dimension operator, right? So but you have two field, then it's much easier.
And no scale.
No scale, no hard dimension operator. So let me give you that. So this is one term one kind of model people study a lot, which is so-called a complex scalar extension of the standard model, right? You put that, you couple to the capital Higgs is H is Higgs doublet. Then you just put a so-called some people call it a Portal coupling, right? And this phi is a dark matter particle. If you want to make it stable, because there is a global U1 symmetry, and then Higgs wave will provide its mass. So studied a lot in the literature, right? So okay, so I mean, I don't want to get into those ordinary Higgs portal dark matter, but in general, there is some constraints when you take the abundance into account, the radical abundance into account, and also derivative detection, all kinds of constraints. And for this ordinary particle with as the candidate of dark matter based on this very simple Lagrangian. Okay, so that's has been done. But the question is like the dark matter could be not just in the ordinary vacuum, for instance, the electroweak breaking vacuum, which you can do this kind of find a way to match to what Coleman was doing. So let me just go through that because now you have two fields, right? So you have the Higgs, you have the complex scalar field phi here. Then you get an equation for motion, and for Higgs you just make it time independent, just a flight profile. And for the phi field you still have this frequency, right? And you put the boundary condition. You have the Newman boundary condition at origin, and no field at infinity, and Higgs wave is ordinary wave at infinity, right? So then you solve this.
You didn't put the quality term for the phi field.
I will do that shortly.
No, it's not bounded from below your boundary condition.
Yes, I will do that. I will do that as well. Yeah, don't worry about that. I will just first give you the simplest case, then I give you also the that term, for example. So you do that, you solve, then you get a Higgs profile, just the solid line, some specific charge, whatever charge. So usually you solve this numerically, you don't get an exact integer charge unless you dial your field value. So you can say that this phi field, which is your scalar field, its density has a little bit this kind of core structure, right? And dies off, and they are interplay. And this is exactly solution of the classical equation of motion. And also sometimes around like some charge, like Q20, you maybe get even two different solutions. Some solution is a little bit flatter dashed line. Some solution is like a dotted line, and then you have a kind of a same charge. You have a potentially have two branches of solution. Okay.
Sorry, the Higgs field is taken here in the unitary gauge, so it's
in the unitary gauge.
So
yes.
It's like two fields. One is real and one is complex, right?
Yes.
The model is two fields.
Yes. Yes. The phi is a complex field. Yeah.
And the potential is renormalizable.
Is renormalizable. Yeah. Phi is a singlet. Complex is key because the Q ball you need a U1Q, which is you need a global charge for that. And okay. So for one point is like you can keep increase Q, right? You can say up to some radius. This radius will be depends on how large of the Q you have, and then you have some region which is electroweak is restored, for example, inside this state, and because of the interplay between this complex scalar field and the Higgs field, and so you can say that even that very simple Lagrangian, you get a very interesting state. Then you can also check what is the stability. So what I'm showing here is this kind of a Q-ball state and minus free particle state. And after you subtract the free particle times the same charge. And if it's below 0, then this Q-ball state is more stable than free particle, and otherwise it's not. And you can say that it depends on the parameter, the Portal coupling, then you have a specific some stability charge, QS, Above that, this cue ball state is stable, and below that, it's not stable, but still existence of this state. And as what you can see, that there is 2 branches of solutions, and for the upper branch is just unstable state. Usually we don't, for this purpose, we don't care, but still they exist there. Okay. So,
may I ask you a question about these extra fields? They're complex, right?
Yes.
So
Yes.
there is another U1 symmetry. There are 2 U1 symmetries.
okay.
They are not coupled. They are not. This U1 is not gauge.
Not
It's
gauge.
global.
It's global.
It's global.
Yeah.
Okay.
Yeah. Yeah.
So this stability, is this classical stability? Or
Because you first, people also check the linear, or we can check the after either perturbation, right, to say whether.
Yeah,
But the simplest argument,
which fields?
yeah. But the simple argument is this is the lowest mass per charge state. There is no any other state can for this state to decay under the assumption that U1 is unbroken.
Yeah, but if it's made out of the Higgs field, it interacts with other fields, or there can still be some kind of charges.
But the charge, this global charge has to be conserved. You see what I mean? So the global charge is additional symmetry of the standard model, right? In this model, there is U1 phi symmetry, right? You see what I mean? There is U1 phi just for itself. No other standard model particles carry U1 phi symmetry. So therefore, that U1 phi symmetry has to be conserved for any process you have, right? So therefore, you need to have this kind of a Q conservation for any process you have.
In principle, you can emit particles, right, which also carry this limited Q charge.
That's right. That's right. That's exactly the subtraction we are talking about here, right? So you compare free particle with the same charge Q, then if this mass is lower than same quanta of a free particle, then this is more stable, right? Get it?
Well, but the phi field being coupled to Higgs, they change through loops, the mass of prediction for the mass of the loop, right?
Okay, good.
I
So-
think you can say that classically it is stable, okay? So this argument is fine, but it is fine classically, right? But once you consider quantum mechanics,
You just
tunneling.
but also gravity, right? You're ignoring gravity.
Yeah, sure. Yeah.
All this gravity is much simpler. I mean, if you have gravity, you don't even need to introduce another field, right?
Exactly.
You can just make it with a quadratic potential, and there will still be self-rotating Q-ball with single field.
It
Charge
makes
global.
a quantum mechanical argument because
Yes.
the charge is conserved,
Mhm,
right? So, yeah, the most you can dissociate is lump into n particles of the mass m phi and the single charge.
Well, there are, as you know, there are no global symmetry.
Yeah,
Global
that's
symmetries,
a
if you
separate issue.
include gravity, right?
That's a separate.
Okay. Yeah, but sorry, even either, let's say, Planck separate operator, in principle, we can still calculate or estimate what's the lifetime for
Yeah.
this. Okay.
And it's within the lifetime of the universe.
I think it's Q dependent. Should
Oh,
be.
okay.
And,
So you can find a
yeah.
Q that makes it.
Yeah,
monolith.
I don't have the number right hand.
You could just have a discrete symmetry.
Oh,
That's
yeah,
enough, right?
that's
I mean, okay, it
enough.
has to be discrete gauge symmetry and quantum gravity allegedly, but who cares? There's not much difference. Gauge. Discrete symmetry. Sorry.
Yeah.
Also, in principle, there could be decay of one large Q ball into, say, two smaller Q balls, right?
The answer is no, even though I probably didn't write down formula, but eventually you calculated the mass. And so here I was writing for this model, but for
the curve is
Yeah.
convex or
some
Once you're away from the minimum, it'll cost you energy to do that.
so yeah, sorry, what I mean is you put a is this correct? Yeah.
imagine you take two small Q balls, you add energies, and it turns out to be smaller than the energy of large Q ball of this charge, which is the sum of the two charges, right?
Yeah, but there's gonna be a minimum. I think what he's saying is there's a
The
minimum.
shape of this curve should tell us whether you
Yes,
want to
yes.
far left
Yeah.
or you
Yes.
want to small.
Yeah. Prefer, yeah, very good.
Yeah,
Maxim.
you-
Either prefer to have large, go to large Q, then you have a gain by
Does
energy.
this turn over?
No, not for this model. No, there is not.
So.
yeah.
The larger the Q.
The larger Q, then you better you gain by energy. And, so for this curve, yes, very good point. Just like a curve is okay. So one thing is like here, we have the self interaction of the complex scalar to be 0. So we have some kind of relation between charge and mass in terms of the size. And but you still have the mass proportion to the charge to 3/4 power and so on. But now we can also add a self interaction. It's a little bit more complicated to calculate, or I want to convince you it's a little bit complicated. But there is one way you can think about it. So now you have this cortical coupling of the self interaction now. And so in general, that costs energy because what we have this some profile, right? There is a phi field in the core, which is large, and this phi to the 4th power. So that's like potential energy. Then you don't prefer to have a very sharp rising. So in somehow the short answer is just flatten out and of the core. And but just let me go through. Probably that's too much, but you can use some kind of conditional. If your field is times the portal coupling is let's say above the Higgs mass, right? So there's kind of interesting play between this. If that's above the Higgs mass, you kind of restore. You know that the Higgs wave prefer to be 0, but otherwise you still have some phi field dependent wave for the Higgs field. Suppose you do that very naive, simple mind calculation, and then you construct this kind of Coleman's effective potential, right? And then you get some structure. And so here I just show you that you can plot that effective U function as a function of a field. And if you don't have the cortical interaction, we can call it like 2, where only have a quadratic. Then you just you pretty much can go any height. So you can think about this is a one particle motion in time and way, and you have a put a ball and roll it down, and then you have a friction to slow it down. But you want to shoot towards at a far infinity time, a future infinite time to stay at this origin. Basically, that's a Coleman's usual trick to deal with tunneling, to deal with this Q-ball method.
May I ask you a question? So your structure, your construction leads to lumps in the dark matter, right?
Yes.
If there are many, if there is 1 or 2 Q-balls, we don't care. But if they are typical, then the dark matter would not be at all homogeneous, right? It will be very inhomogeneous.
Yes.
Doesn't it have an impact on all predictions you people obtain now for the dark matter? There should be some like propagation from dark matter.
Yeah. So
some visible.
Yeah. That's what I mean. Yes. So usually we have a say 100 GeV, right? Dark matter particle. So we have the density. Let's say local density is 100 GeV. So that's the density. So you have an ordinary 100 GeV. You have a separation distance like that, right? One particle drop. So suppose now for this big object, let's say 10 to 22 GeV, right? For the Q-ball, for example, right?
Okay.
So basically you definitely separate that a lot, right? But you separate only by cubic root of this mass ratio, so which is around 10 to 7, right? So ordinarily you have like a around 1 per centimeter. So you have the distance to be around 1 centimeter. So now you have like a 10 to 7 centimeter. I'm saying that that's not observable. We have not yet get into that inhomogeneous measurement.
So you say that this granular structure is still not granular enough to be observed.
Yes, unless you make it like a solar mass, sure. Then we can start to, or planet mass, then we maybe start to see the granular effect.
But this forms during electroweak phase transition.
For this model, yes. Yeah.
That's the idea.
That's the idea. So even though I have not get it. So basically the interesting thing for this model is you only need one coupling. And this coupling, you also can have this phi particle generate a common Weinberg potential for the Higgs. And by doing that, you can also check the final temperature of the electroweak phase transition. You will have that to be first order, for example.
Or else it changes the
yeah, you change the Higgs potential and change the phase transition. Then this one really can have a little bit more complete story to even form the object you want, which I also get it later.
But assuming that they have form, you can also probably calculate their finite size, right?
Yeah.
Because they would coalesce to a point, so when they don't no longer meet, right?
Yeah. those things has been done in previous paper, in my previous paper for this model. Okay.
Right after this, you were making the point about the quartic
That's right.
coupling.
Yes.
So I missed, how big is your quartic coupling relative? So you hear, this is for, how does this picture change?
I get it. That so yes. I think it's a bigger change in terms of the profile shape. And maybe I just
you can't ignore the quartic coupling.
You cannot ignore the quartic coupling
because you get it from loops anyway, right?
I agree with you. So eventually we should take the cortical one to be more serious. So previously I give you some profile, right, for the scalar phi field profile without quartic coupling is like a very cuspy, right? So there is a huge spike, right? But now with the safe interaction, and then you basically flatten that out, and but you flatten out in the following way, and you increase your charge, and you slightly gradually decrease the frequency of this particle, and that frequency has a little bit of a symptotical frequency, which is a very simple analytical formula in terms of those cortical coupling and the other coupling, and then you just pile up. Then you push it, you don't change this height anymore for the inner core, so you just pile up. It's really like matter now, like ordinary matter. You pile additional quantum number and make the radius large, and you don't density does not change anymore. For example, in the inner region. So that's another thing which maybe my limited knowledge, I just found like that's a very interesting way for me to understand some two types of Bose-Einstein condensation. There one case you ignore the self interaction, then the core density can be arbitrarily high and up to a level, and then you have some relation between mass and the radius, and then another type, which is the cortical self interaction is important. Then you flatten out, then you get a slightly different relation between the mass and the charge, and now you have really the mass proportion to the charge and some intrinsic scale in the problem. And so yeah, we should take this with the cortical interaction to be more serious. And
so this case, this case with the self interaction, does it mean that this table can decay into two smaller tables?
So the I see. So still you gain binding energy, and I tell you why. Because once you push it to large charge, you can see that the radius become large, and but the intrinsic frequency, in a sense, the energy per quanta still decrease, and so you still gain, but not gain that fast compared to the previous case, but you still gain.
It's like energy versus charge curve. It is.
Yeah, curving.
It is shaped this way, right?
You're right.
I mean, nothing. Okay.
Yeah. Which is what he was trying to say. Also, what I was trying to write down over there, and
So I think I'm just looking at this equation, like m is proportional to 2.
Yeah, that's leading term.
Okay.
That's leading term. Yeah.
Important for the stability.
Yeah, that's important for the yes. That's yeah.
And dimension 6 terms. What will they do? By star Q. I don't think he has it. Oh, but you could.
Oh, I see. You could. Okay. I think that will modify this asymptotical field value in the core in some way. And
if couplings are small, they don't.
Sure. But yeah. But just in case you care, that will shuffle around this, make it different.
At least. Whether or not you include it, separately at the tree level, you'll still have them.
Yeah.
Oh, yeah. I agree with you.
Start putting in all.
I totally agree with you. So yes, yes. I think at some point, depends on the relation between those couplings, right? At some point, if you for some reason your self interaction is so small, then you definitely care about the quantum corrective.
Yeah, but if phi h is big, then these other terms are not necessarily going to be so small, because the quartic that you're going to get from the loop is going to go. Well, the first one will go with the lambda phi h squared, and then the next one is lambda phi h cubed.
Yeah. I agree. Yeah. So
you get some loop.
You get some loop. Yes. Yeah. So.
Excuse me, in this picture for dark matter, which seems nice, where are monopoles? We heard about all sorts of.
So now we convince the Q-ball property. Now we say how monopole enter the Q-ball. Okay.
You want to this exotic cue ball being made from
not made. Can accommodate, can contain monopole. That's what I want to.
No, I understand.
Yes,
You
yeah.
first made this exotic
Yes.
cue ball from the very exotic dark matter,
Okay.
specifically ad hoc arranged.
So the
Okay.
data is not it's not so exotic, right? That's maybe the simplest model, right? That's just the scalar.
Okay, but okay. There are dark photons.
No, but this is just a
No dark photon in this model.
This is maybe the simplest one you could
Yeah.
have. Right?
Okay, I don't disagree.
Thank you.
Speak this way 5 years ago, right?
Maxime and Misha, they did it, I don't know, 15 years ago.
Okay, their voice was not heard. Because there were so many people who used LSPs and God knows what, axions. Now we came back many
Well, you can say it can happen, but
years
people
ago.
listen,
Okay,
there's probably
so
hundreds
we
of
have
papers about it.
these exotic cue balls. Now there's exotic monopoles, which nobody knows how to create after the inflation, because usually they are created before the inflation. And they have to get into these exotic cue balls.
Yeah, I will tell you how they get into this exotic cue ball. Okay, so
One last question. So does all dark matter end up in cue balls?
in the previous, the answer is yes. You can calculate. You can. I mean, it still depends on the chart. You can calculate if it's a first order phase transition. You can calculate later evolution of a free isolated ordinary particle, because they have some probability to meet this cue ball state. Once they meet, because their energy per mass is different, so they have binding energy, so they prefer to stay inside of the cue ball to grow the.
That means that they can be cue balls of arbitrary small charge, right? And they're already
charge. Oh no. So you just since you start with some generic Q0, right? So then
you start forming a cue ball. Yeah.
Okay, so let's wait until the end. Then
Okay.
We have already not so much time.
Okay. Oh, okay. So now it's this question is, do you think this Lagrangian is simple enough or not? No, right? So in order to have monopole, I have to talk about SU2 break to U1, some gauge symmetry break to U1. But then I also need to have a cue ball. I have to that U1 global symmetry. So those two ingredients I have to keep. So if you allow me to keep that two necessary ingredients, then I will tell you that then there is interesting object can come out of this Lagrangian.
One U1 is global, the other one U1 is gauge.
That's right. Yes, there is then that. Yes, exactly.
But this is not our world photon, right?
Not in this model. This is a toy model.
Because otherwise, we would immediately rule it out, because all your cue balls will have huge charges.
But the cue ball density is also tiny.
Magnetic charges, they are huge, and of course you can measure it. You could measure it. So
actually,
it cannot be our photon. So you want to have another photon.
So
which is screened, okay, it's screened for fixing, but still the magnetic field is not screened.
Okay, so I do want to have this to
it's
be
a long range interaction of the electromagnetic type, in addition to gravity interaction.
So I just give you one thing. So if I have the cue ball, whatever the object I'm talking about here, suppose its mass is whatever 10 to 20 GeV, right? A little bit heavy, like what we're talking about here. If they carry magnetic charge 1 or 2, unit 2, right, in that frequency, I'm saying that we don't know its existence in the current universe. We cannot measure that.
Why not?
Because the electric charge.
Dark matter is everywhere, here in the lab. If it is our photon, then the magnetic field of our photon from the monopole, it's much stronger than the electric field, and it cannot be screened by charges, right? By creating a pair of electrons or positrons. So if we measure this magnetic field, just put here your device.
I wish to do that, but that's that's the reason I'm studying this object, which is exactly your point. But I'm saying the current situation, given the number density of these objects or dark matter energy density, still difficult. Let me provide the reason. For example, you have the 10 to
Wait
20.
a minute. If it is our monopole with our photon,
Yes.
then Rubakov-Kalin applies. Then if it is right here, it should start catalyze the proton decay. It should start catalyzing the proton decay like crazy with a strong cross section. Would we be able to see that some protons disappear, right?
Misha, it depends on the flux that's coming in.
Huh?
It depends on the flux coming in.
No, but it's, you see, when all no flux, forget about it. We're all submerged in the dark matter.
No, but you have a detector. I need a flux for a rate.
Okay, dark matter moves a little bit here and there because the Earth moves on an annual.
But still need to check that detailed number, right? For example, this mass, which is 10 to 7 centimeter, which means the one dark matter and another dark matter, which is 10 to 5 meter, which is like 100 kilometer, right? So which is far away, right? If you think about it. If you make it heavier, they are more safe.
Okay, but do we take into account that if there is a monopole, our monopole with our photon, it will stay here for a long time, and all time it stays, it catalyzes the proton, and where it disappears, it starts catalyzing reaction of the proton decay, catalyzing with a strong cross section. So you see from some part of the space, all of a sudden, you see when proton decays, it emits electrons, okay, and you should see that, or positrons.
Yeah.
It depends on the rate.
Right.
Depends how often.
So
It stays here forever.
No, why it stays here? Why it stays here? Given this is like a train, right? Huge train. And that even it can easily pass the Earth. You see what I mean? It's so heavy. The Earth may not even have enough, even in taking into magnetic or electromagnetic interaction.
Say you have one very heavy monopole,
yes.
But it is here in our air.
No, but it's flying through the.
Well, some of them are flying. There is a distribution in velocities. Why all of them should fly away?
Because we're flying.
Some of them are slow compared to ours.
It's going to be a Maxwellian distribution, but
okay. If there are at least few of them, you will see it. Believe me. Well, you don't have to believe me. Just estimate. The energy release is huge.
I think he must have done that.
Yeah.
So just T2K, for example, in decades of searches.
So those things like you depends on the mass, and for lighter mass, the Earth can stop, then can accumulate those objects. Then you do care about, for example, the Kalin-Rubakov effect. You even care about opposite charge they annihilate to generate interesting heat from the Earth, for example. All kinds of things can happen. But I'm saying that there's still some that depends on the mass, depends on the charge, and it's model dependent. Because it's not nothing is left in
what is model dependent?
Oh, model just in
terms of section of proton decay is not model dependent.
But to capture those very, very heavy object depends on the.
No, it's the other way around. Very, very heavy object captures protons and neutrons. It's the other way around. It's not the proton which captures the monopole.
Yeah, but they capture on far away. Capture proton.
Far away. If you say there is one, with some probability, it may be one in our. And then it starts capturing.
To know the answer, you're right. There is a number, but you need to know: is it 1 per second or is it 1 per 1,000 years?
Okay, let's hear the answer. I want to see the estimate. I want to see the estimate.
You want to see? Okay. Let me first. Let me just wait 10 minutes. I finish this, then we can go to the estimate.
Just a related question. There would also be a constraint from neutron stars because these things would fall into neutron stars, and then they would be collected and accumulate over millions of years. So, which is the normal limit, the strongest limit on the abundance of monopoles is from the Rubakov-Kalin effect in neutron stars.
Yes, we do. When we check the magnetic black hole, we do take that into consideration, and so it does provide the stringent constraint for. I mean, I'm saying also some range of mass, right? And also depends on what type. If I remember, what type of superconductor inside of the neutron star as well. Which type? There's some little bit of variation. And anyways, that's just a detailed question. But yes, we do to take it into account. And, okay, so now pretty much the calculation is very similar to what we were previously entertaining. And so they have a Lagrangian, you have classical equation for motion, then you can check. So now we have two U1. So one is a gauge. We want to say that is a little q, so magnetic charge. One is global, we call it a capital Q. So we want to say what's the state looks like for different little q and a capital Q. Again, for little q equals to 2, we can do spherical calculation. We can write down equation of motion explicitly, otherwise we cannot, so which we don't know how to solve. So this one we don't care. So some equation of motion, 3 coupled differential equation, some boundary condition. Okay, so just give you some solution, right? So if the little q is 2, the global charge is also small, q equals to 2, and you get some solution like this. So you can see it's a little bit overlapping. There are some solid line, there are some dashed line, and the solid line is the one which we are which without a q capital Q equals to 0, just ordinary monopole. Those are gauge scalar profile and the gauge profile. That's ordinary monopole. So now we add a little bit global charge for this monopole. You don't affect the Higgs or the gauge field that much, and but you do have a little bit some profile for this complex scalar, and so that develops some. So you can also understand a little bit. Instance, there is intrinsic. There is 1 over mw, right? So that's order 1 unit using here, and that's the monopole radius. And but when you have a very tiny global charge, the scalar complex scalar field will be just also match to the monopole radius, and for this one. And okay, so that means that in this limit, the global scalar charged scalar particle just follow the initial monopole profile.
What does it mean? BQ equals 2. It's not. So you have basically 2 particles. So you have Q balls formed out of 2 particles, right? What does it mean Q when capital Q equals 2? So it's Q ball.
Q is just the charge.
Yeah, so you have 2 particles.
You could think about the free particle is just 2 particles, yes.
But still, you think of it as classical solution.
Is it related to the?
Yeah. Just the exponential I omega t related to the time, the frequency, right? So you use that to define.
But I mean, Q, it's like if it's 2 particles, can you really think of it as classical solution? Because for classical solution, occupation number to be big, right? That's what kind of.
So that's also interesting here. So you don't need that. If you have a monopole and put a individual 2 quanta or even then you.
So it's not a Q ball, it's a monopole.
It's you already have monopole there.
Monopole
so this is other way around, right? So the monopole is there. You put a free particle inside. They develop this kind of non-trivial profile and behave like a soliton instead of a free particle, right?
So the monopole captures 5 particles, right?
In this case, yes. You can think about it in that way.
Interaction of the 5 particles are only through Higgs, right?
Yes.
But it should be very strong in order to be captured, right?
Yeah, order 1 in cortical coupling.
Yeah. So it's not a weakly coupled calculation, right? Not weakly.
No. Oh, I see what I mean. So weakly coupled in terms of the perturbativity is still weakly coupled for all the coupling where I'm choosing here. And all those coupling is smaller than, for some cortical coupling is smaller than 4 pi square, right? So that's 16 pi square, that's the perturbativity.
But then how do you get a bound system? It's not necessarily. If you have a scalar particle, scalar exchange of the scalar particle are attractive. If it is diagonal, here it's not even diagonal because it's an interaction between the core of the monopole and these 5 particles.
I don't know whether yes.
Let's assume that it's attractive. If in the range of small parameters, it's not binding. Right?
Yeah.
But you want to keep your 5 particles localized inside the monopole. This is doable in principle. If you make lambda strong enough, but then you are outside the weak coupling approximation, and
I'm very curious because I have an electron positron from bound state, but the intrinsic coupling is still perturbative coupling. I still can talk about the bound state, right?
yeah, but it's very large, and you want to have it your phi inside the monopole, and the monopole has radius of order 1/mw. So in order to have bound state in the Coulomb force, you have to agree that they are, in some normal sense, are very broad. I mean, the wave functions, as you know, the Compton wave of the.
I think yes. Can I answer you?
Huge compared.
I see what I mean. Can I answer your question? Like we are not talking about non-relativistic bound state here. We're talking about a little bit more like a relativistic bound state.
I think what we can say here is that we have a classical profile, right? That creates kind of potential for this Q particles, right? And then we want to think about the small perturbations, right? So bound state, but then the size would be inverse the Compton wavelengths of the Q particle, right? And we should compare that with the size of the monopole.
Yes, you have to have them approximately, well, similar, right?
It does, right? So it does, right? So if you think about you have a monopole, right? So what means there is a Higgs profile, right? The Higgs profile, we were just saying that it's just showing on this plot, right? So it's some kind of at origin is 0, right? So symmetry restored, and at infinity is a wave, right? For example, let's just simplify this picture to say this is a step function, right? Okay. So when you think about this is a step function, now you ask this is a potential wave, right? And make it a little bit more like symmetrical way, right? So you have the S particle come in, right? So S particle in the ordinary vacuum, so you have the mass ms squared equals to whatever the coupling over there times the wave square, right? So now you pass under it here, right? So you realize, oh, actually in this region, the mass, the wave is 0, right? So the wave is 0 in this region, right? So you definitely will see this kind of potential wave, and then you can do this kind of quantum mechanical scattering calculation to talk about the bound state formation, right? For example. Okay, so that is the small capital Q. In the large capital Q, it's the other way around, and which is kind of the one thing which kind of the motivation we want to get. So if the Q-ball charge, global charge is very large, then you have the first you look at this scalar, the complex scalar field, S field. So you have this curve, and this radius is determined by whatever large charge you have. Then you push that to up. And then you can see that the Higgs field is going to here, so they are restored in most of the cases. So before you look at the green curve, and that's just like ordinary Q-ball situation, and with the self interaction, so you have almost like a symmetry restoration inside the Q-ball, and then there is some boundary, and there's some transition of the boundary. But now you can look at the gauge field. The gauge field has been dragged by whatever the Higgs field profile, and then you really have this gauge field extend to the same radius as your Q-ball radius. And think about it, like at the beginning, we were talking about this energy, right? The B square and blah, 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 and the magnetic energy. But if you spread that out, you basically downgrade the magnetic energy for the monopole part, right? So that's the reason. When you have this monopole, now you can think about this is a monopole inside the Q-ball now, right? And the monopole really gains some kind of binding energy. The magnetic field is more spread out, and as a result, they prefer to stay inside the Q-ball and instead of isolated monopole. So that's kind of the simplest intuitive answer. So all those plot just solve that numerically, and you get this one. Okay. Okay. So let me ignoring those analytical calculation in principle, you can analyze this in some simple approximate analytical way, but eventually you will get, for example, in this notation, right? So you have this kind of magnetic charge is 2, global charge capital Q. You can have a free monopole, magnetic monopole. You have a free Q-ball. You can calculate what is the mass difference, which is the binding energy you gain, and if that's positive, right? And so this one is the ordinary magnetic monopole mass, which is 4 pi V over E times some order 1 number. And then you can just check there's some numerical number, but forget about that. But eventually is when the global charge is large and this term is very small, you really gain the binding all the binding energy or almost like the monopole mass will be approximately the binding energy in a very large capital Q limit. And so that's basically what's get into here. Okay, so now, I mean, then you can check other possible decay. You can have the this decays to free particle, right? So when we talk about the Q ball, we also check that. You can also have the decays to Q ball. We already discussed that. You can also decay 1 particle, for example, free particle. You can check the stability of all that, and you will find that the most relevant one, which is a Q decays to Q particle, and then you can just calculate under what condition, what is the ratio charge you have, global charge. Then in order for this object to be stable and so on. But in general, it's stable against the decays to isolate the Q ball and also 1 particle decay. And so anyway, so that's just some detailed calculation to just give you some idea of generic parameter space. Then you can have this this object to be stable. All on the right region is stable, and when you get to the gray region, then if the charge is bigger or than 100, then it's stable. Otherwise, it's not stable. So, and this is the interaction portal coupling between the Higgs and the complex scalar. This is the gauge coupling. And one thing I just maybe just do on, suppose you fix the portal coupling, right? Just look at the vertical way. You can see when you increase, when you decrease the gauge coupling, right? When you decrease the gauge coupling, somehow you make the monopole size, isolated monopole size larger and larger, because that's 1 over MW, right? The MW is E times the wave, and then you make it somehow more stable, and vice versa. So you can check that. So probably time constraint, I don't want to do on that much. And because of that, then we can think about we can also put a more magnetic charge inside of the Q ball, and by doing that, you can basically think about that because of the spread, like what I was saying there, right? So the gauge field will spread till whatever the Q ball large radius you have, and then you can count the magnetic energy, and based on that spread, then you have this to be 1 over the Q ball radius or this object radius to count the energy there, and by doing that, you will know that if the relation between magnetic charge and the global charge satisfies some kind of Q and the Q1 cubic relation, then those magnetic little Q magnetic charge can be contained in this Q ball state. And so that's kind of the message. And then by doing that, you can set some lower bound for this state's mass. And
didn't you say that monopoles with Q bigger than 2 are not spherically symmetric?
It's not. So which means we need to put a wiggle here for this part. And for the previous part, Q equals to 2 is exact, at least solving the classical equation of motion. Yeah. But for this one, we can only use that understanding to apply to large little Q. Okay, we still say, oh, it's approximately spherical, and to put a wiggle there.
Use large, it's approximately spherical.
Yes, which is not as rigorous. It's just we don't know the precise number of those things. So, but at least once you intuitive understanding of what's going on, then I think this is trustable. Okay. Okay. So at the end, what I want to say is,
now you're going to take the
no.
Gravity of the spores.
That's a
Q ball in the monopole, and now you throw
the whole thing in a monopole, oh, in a black hole. Yes, that's next year work. No.
Excuse me, if I just, it's my last question, because at 2 o'clock I will have to disappear forever. Maybe.
No, not forever.
My last question, if you already use this sector of the model, which is good for monopole, why do you need dark matter? Create them, because anyway, this have to be monopoles created after inflation, okay? Create them right now, everywhere in the universe, near Earth, away from Earth. So there will be many dumbbells, Nambu dumbbells, just in the standard model, okay, without any modifications. They are unstable only quantum mechanically through the monopole anti-monopole pair creation, and it's
not stable. It's very short-lived for the dumbbell, monopole, anti-monopole dumbbell, right?
No, of course they can annihilate, but monopoles are very heavy in the scale of the tension of the string which connects. Tension of the string is V squared.
But the intrinsic scale is electroweak scale. But the intrinsic scale in that case is just electroweak scale, right?
No, I am telling you the answer. The tension of the string connecting the Nambu monopole and anti-monopole is of order V squared.
Okay.
And the mass of the monopole is what? The mass squared, or the mass of the monopole is V divided by E squared or G squared, right?
Okay.
So if you now try to estimate how much you need you take how this occurs. You have the string, and then a part of the string annihilates, but this part of the string should be enough for pair creation. So if you look, it's a you have to collect energy from a long part of the string. This is a tunneling process. It's okay. It goes, but it goes exponentially suppressed as any tunneling process in quasi-classics. It's not classically unstable. Classically, it's a stable configuration. But
why is that? Because you have this string, you have the force between monopole and anti-monopole. Classically, you just no.
Estimate. Okay, there is a tension. Okay, tension is very weak compared to the mass of the monopole. So the monopole acceleration will be very small. If originally the string is of a noticeable size, not very small, not monopole, anti-monopole, just on top of each other.
Right.
Then accelerate the velocity they will need in order to eventually, come to get it out. It takes a lot of time to accelerate a very heavy object. Heavy objects don't want to be accelerated by a limited force. So if your classical annihilation.
So you said the tension is
V squared.
The mass is 4 pi V over E, right? So what is the time scale in terms of
over E squared?
Over E squared.
Because it's the mass of the monopole divided by G, and the mass of the if you multiply, you see any soliton in natural scale, yes, it has E squared. So it's the mass of the monopole divided by E squared.
Right.
Okay, you wrote it not in terms of the mass, it's V divided by E. Yes, that's correct.
Okay. So now my question is, what will be your estimation for the time for them to merge, for them to annihilate, to meet?
Well, the force doesn't have one over. Assume that E is academically small.
No. E is order 1, right? In the standard model.
If E is order 1, you have no parameter.
That's what I'm saying, that it's just an electroweak scale. I don't see any way for that to be long-lived.
If E
is
a small parameter, there is a difference.
It's a tenth small.
But it's a dark sector. You can have.
It's 1 over 10.
No, this is not dark sector. This is the.
You mean E?
Yeah, E.
E is 0.3.
Yeah.
Well, usually there is this 4 pi, so I don't know how 4 pi.
Sorry, just I think Lambu estimated the lifetime. So in his paper. So
I'm sorry.
Okay.
Sorry for asking questions.
No, very great.
Your ideas were very interesting, but unfortunately,
no problem.
they don't disappear now. It will be not good for me.
So, okay, it's just a few more slides, just then I finish. So then just to give idea, there is some mass, right? Depending on the intrinsic scale, because we may not necessarily have electroweak scale, then you can populate those states to be above this line. The other states will be populated. But if it's got a scale, you populate above that. But you can say it also kind of cuts off by some hashed region, because if you get into that region, the size is so large, they already form black hole by itself. And because the radius is comparable to the Schrader radius, and then you also don't have that. Then just become. But the point is, you have the extreme black hole, magnetic black hole, for example, right? So which is the one I was talking about at the beginning. There are some other black hole physics you don't care, but for ordinary physics, extreme black hole, we know that one reliable or but a little bit weaker constraint, which is a Parker limit, and which we know that the fraction of dark matter cannot be magnetic monopole, and also apply that to magnetic black hole, then you don't have that to be account for 100% of dark matter. But if you have this kind of a little bit independent mass and Q-monopole and charge, then in principle you could populate some region here. Then you principle you could have a some magnetic object heavy, but also account for 100% of dark matter. So anyway, that's a little bit simple point, but just a very, very simple about the production, right? So one production, you could have a first order phase transition. It's also kind of interesting, and there's lots of things has to be done. For the Q-ball formation, you can say, oh, I have the high temperature, I have in the unbroken phase of whatever Higgs Electroweak, right? For example. And then you start to form some like a bubble of the global vacuum bubble, right? Out of the metastable or whatever initial vacuum. Then those bubble, then you also have those complex scalar particle support, right? So they are thermalized. And then you can see that because they outside the wave of Higgs, for example, is 0, so it's massless. But inside there is some wave, so then it's massive. So if you think about those bubble and meet those quanta of the particles, they will kind of pushed, squeezed into a smaller region. May not be so 100%, maybe there's still something left over, but just give you a general idea. And but once you kind of finish your phase transition, you just turn around. You say the blue region occupy most of the volume now. You turn around, you look at this intersecting point, then that will become some region. You have a high charged charges, global charge in that region, which is still potentially in the previous vacuum or symmetry not broken. And then it's just a matter of they use quantum pressure to hold that vacuum pressure to give you this solitonic state. Okay, so that is just a cartoon picture, but you can get into the calculation. But now correspondingly for this object, we are talking about a Q-monopole-ball, right? So we also need to talk about topology charge. So for the topology charge, then you generally, you say you have some region, some bubble, or when they meet, there's some generic size, some separation distance, there's some phase, then different bubble, in general, you anticipate they're not correlated, random phase. And you can estimate what is the probability to have a winding number 1. And in 2-dimensional, that's like 1/4. If it's a same size bubble, and in 3-dimensional, you need a 4 and tetrahedral kind of a construction, then that is 1/8. And so in principle, you generically anticipate either form some Q equals to 2 charged monopole Q-ball or not. And most of the cases, you still just have a no magnetic charged Q-ball and a small fraction with magnetic charged Q-ball. And you can also say that if you want to form much larger magnetic charge, it's a little bit more difficult, also kind of interesting. So in terms of 4 bubbles in 2-dimensional plane, you cannot form winding number 2. You need to have a 5. I just give you one example. So you can go this direction, go back, go this direction, go back, and go this direction. You have some 5 star. Then you can circle a point twice, and so you need a 5 bubbles in 2-dimensional to meet each other. In 3-dimensional world, it's a little bit more requirement. But suppose in 2-dimensional, you ask, I just throw some random center and the equal distance to ask the meeting point. You can see that the majority of the meeting point is like 3 bubbles to meet. A very tiny fraction maybe has some 4 or 5, and so which tells you that in this first order phase transition, somehow it's a little bit not that easy to form those large magnetic charged object, which just means that most has to be done to also check their later like Boltzmann equation to say whether they will meet later stage after the formation. Okay, so that's So generically, you can plug that to ask under what condition you can have this object to account for 100% of dark matter. So maybe I just dwell on this one. In general, you can have two situations. One is like so for that global charge, for some reason you have some asymmetric initial charge, so which you don't know what some other physics to explain that asymmetry, call it eta q. Or the other case is eta q equals to 0. So with pure symmetric universe, symmetric universe, you still have a chance because generically you anticipate some charge because now what you have a total number of particles in Hubble patch. You have number of sites 10 to 13 from your first order phase transition calculation. Then you divide it by that, then you estimate what is the average charge inside each site, inside each pocket, each ball, right? And if it's a symmetrical world, then you just say, oh, maybe you have a square root of n possibility variation variance to anticipate maybe that's a square root of 10 to 33. That is some typical accidentally asymmetric charge, and you could have that to show up. But if we put that and basically tells you that depends on which situation, you maybe need the scale to be whatever 200 TeV if it's pure symmetric, or otherwise you can have a symmetric one. You can have a lower scale to explain all the 100% of dark matter abundance in this specific first order phase transition. And there are also maybe more story can be done in the second order phase transition, which I just end up here. There's also skip the Dirac detection, and obviously once you talk about dark matter, you can talk about Dirac detection, which is a little bit different because it's so heavy, right? And let me also skip that. Let's just conclude. So basically, I just want to say that some kind of motivation, our simple-minded goal is trying to get a large magnetic charged object. Then we get into this kind of reasonable simple model. We find a solution can have some soliton with carry both topological charge and the non-topological charge. And also just to identify this, we call it a Q-monopole-ball, which can be another object similar to a magnetic charged black hole and carry large magnetic charge. And I give you example, and you can from first order phase transition to account for all the dark matter abundance. And once you have that, then we can also find some new ways to search for those objects. Okay, thank you. Yeah.
Thanks, Yang, for the very nice talk. And we have many discussions already. And let's see if any quick questions. And then there's also time for us to stay longer with Yang.
Well, just a quick question.
Yes.
What's the best way to discover?
That's a better way to discover two ways. One is Dirac detection, because you have if you have Electroweak symmetry restoration, almost like you use geometric cross section, and so which is plotted here. But you need some big detector and to look for that. That's one way. Another which is you rely on the it has magnetic field, magnetic charge, magnetic field. So one way we thought about is Earth's magnetic field or Mars magnetic field to see whether any monopole object inside. Another which is maybe there are some device like ordinary that discovery of the monopole, right, in one event, and which is using some magnetic aluminum detector, for example. And so those few ways we were trying to check what's any possibility.
Just to clarify, so if you have this monopoles with a standard model magnetic field and which are separated by this distance 10 to 7 centimeters that we discussed, and they make all dark matter, aren't they allowed by, I don't know, searches in superconductor handle or something? It's still possible to have such monopoles.
Oh, I see. So the answer, I don't think I presented that here, but I think it's still how do I say, if you don't fix to one specific mice, and then there's still some mice has not been covered by those searches. Okay,
so they can make 100% of dark matter.
Yeah. So that's a difference about what is it, like the Parker limit, right? The Parker limit is a little bit independent additional story, and so that one for the extreme black hole you have a fixed relation. So that's then you cannot have this object to be 100%, and so that's why we kind of motivate us to think about some other large magnetic charged object to see whether that can be allowed in series space first.
Okay. Yeah. No more questions. Thank you.
Yeah. Oh, just mean that. Oh, I see. So just mean that not the even for Xenon 1 tongue, it's not their single hit search.